Greetings, welcome. So in the last video I was talking a bit about this issue of spin loss with the pulse motor and with electric motors in general, and are there things we can do to mitigate it and whatnot, or what can we do about it? And I thought I would just kind of show you this spin loss, and just real quick here. So we have a Hall effect sensor down there, and that Hall effect knows when a magnet's coming past, its state changes. It's going to an Arduino. The Arduino is saying when to turn this coil on depending on where the magnet is so that you get rotation, and it's only doing so with brief pulses. This is all just sort of arbitrary, but we're spinning at 797 RPMs and 6 volts and maybe 10-20 milliamps, and then I have a meter hooked up there in terms of what we're getting back from the collapse of the spike here. Now if you just take a coil, just put it there, nothing changes. If we go back here, come on, do something. It's showing 794, but essentially unchanged. 792. We were at 797 before, and I think it's just that it weighed the plate down a little and brought this coil in a little bit closer. So a little bit more spin loss. It's not coming from there. But the reason it's not coming from there is a voltage that's being generated, but the voltage has nowhere to go. And if instead you say, like, put a diode on here and rectified it and then put it across a load, a resistive load, an inductive load, and caused it to do work, then you get a lens reaction, and that lens reaction is in opposition to the rotation. So there's nothing new about this. It's when you load something, it slows the motor down. And to just give a really dramatic example of that, I'm just going to connect both of these wires together. So the only resistance across here, I'm not going to bother to rectify it, but the only resistance will be the resistance of the wire. And now that current has somewhere to go. So I just connected those wires. You can hear it slowed down. How slow is it going to go? We were at 790 whatever. It's slowing way the heck down. It might not, well, it should be able to spin, but it might be at like 100 RPMs. I'm going to see how far it slows down. And again, that's because that thing's trying to do work now. The just voltage is flowing from one end of the coil to the other. The other thing you can note is the amp draw is now like 4 times as high. The duty cycle hasn't changed, the percentage of time this thing is on or off. However, because of the reactance of the coil, the longer pulse allows the coil to saturate more, reducing the reactive resistance in your drive coil. So what are we at now? 353. And it seems to be wanting to stabilize there. So it more than cut it in half. So I've removed that load now. We'll let it spin up. But I'm saying that you're getting the same effect going on with your drive coil. And it's sort of, well, how can that be? This is your drive coil. It's not your pickup coil. And it's having current go in, not the other way. So why is there spin loss? But you can see it, and I demonstrated this a lot with the air gap, where if you move the coil up here, instead of that thing spinning at 790, it'll be spinning at like 1,000. Eventually you move it too far away, it won't interact. But the spin loss begins to get to a point where the rotor is even slowing down. However, the amp draw goes down as the rotor slows down, which is curious too. As I was saying, so that's all very curious. But what's going on? So let's let this thing fully spin up. Okay, well, let's look here. We're up to 787, it's climbing somewhat slowly. I think we were 790 something, 797. So we'll get back to there, but we don't even need to worry about that. So what I'm going to do now is I'm going to turn this down to 0. 1, 2, 3. But it's not at 0. It's at 3.5. Now, also, this is at 4.5. It was at 13.4 before. Now what's interesting there, and it's just gradually spinning down. I'm going to turn it back up. But that's your back EMF. And that's why the amp draw goes down, because there's actually only the difference between that back EMF and the voltage that you were set at that's driving the thing. Okay, so I've spun it back up, and we're back up to like 790 or 800 or whatever RPMs. And we're at 13.4, 13.5 volts going into here. Now again, I'm going to just turn this all the way down. It doesn't go down. This goes to 5. Now, what's interesting about that is that teases out the relative components. That's no longer from the collapsing magnetic field. That it's slowing down, so that's going down. But that 5 volts was from the magnet spinning past. And then you had 8 volts from the collapse of the field. So I just think that's kind of cool. And I haven't looked at it, in different axes, but you can kind of tease those two out. So let's crank it up here for a minute just to get it spinning again. And then just to show you that I am doing what I'm saying I'm doing. So, you can say, well, you're not really turning that all the way down. You're just turning it halfway down. That's why it's reading 4.8. Okay, so maybe I can show both of these at the same time. And I lift this up. Boom, 0. Boom, 0. Put it back. Boom, 2. And we were spinning faster. Nothing. Back EMF. And some of that back EMF goes along with the collapse of your inductive spike out there. Okay, let's spin it up again, and I want to show you one other thing. So we'll give it a minute to spin up. And this time what we're going to do is look at amp draw when we turn that thing down to 0. Okay, I think that's fast enough. Now, turn this to 0. If you can see, it's trying to go negative. Now, you might say, oh, no, you're not. All right. How about this? Now, see what the amp draw is doing? So that amp draws that way. Now, do this. And it's not made to show negative, but it's below 0. And now it's stopped. But I was starting to build the bipolar commutation circuit, and I thought of one thing, there you go, thinking again. And I thought, well, it's worth looking at. I didn't think it would make a big deal, but I thought maybe it'll help a little. It turned out it didn't help at all, but it's still just worth mentioning. So how the heck is this thing getting back to source? And before, I was only using one switch, and so you would have let me get a pointer for you. Not that. So you have your positive bus line. It comes to here, and this goes into there, and then there's a switch to there, and that's where your one end of the wire was going, and then I was just feeding it back to negative. So I thought, well, it's worth making and breaking both the positive and negative legs, and so I put in a second switch there for the negative leg. Goes to there, and then when that switch connects, it goes to there, and that lets it go to negative. So now you're making and breaking both the positive and negative legs. So if we go to the Arduino code for this, it's just you know, a few more lines, and just saying that pin 13 goes high, pin 12 goes high, pin 13, pin low, pin 12 low. So that breaks both positive and negative. And, you know, I tested it that if either of them aren't, you know, functioning, if they're always low, then the thing doesn't run. And so it is doing what I think it's doing. It's making and breaking both legs. So again, as I was saying, how does it get back to source? And the way it gets back to source is when the switches are closed, you have a connection between here to the positive and here to the negative. So it goes back, and that's your load. And that's why it slows down, because it's shooting back to there, and you don't particularly want that. But I thought, well, it's, you know, worth looking at. If you make and break both legs, maybe it'll at least like mitigate it. I couldn't see any difference, and the reason being is that, okay, and everything I showed you was with this setup of making and breaking both legs, um, both positive and negative legs. That even after you shut it off, I mean, it still makes and breaks a path back to here. And in order to make this thing run, it has to make and break a path with the magnet near the rotor. And so since the magnet's near the rotor, it generates electricity in here. So I thought, well, maybe, you know, maybe it would be 5 or 10 or 20, or, you know, I was hoping for like 40% better. I can't see any improvement, because it is now, you know, entirely disconnected when it's shut off. But it's just that you have to turn the thing on to pulse it with the magnet there. And so so you can't just do that. But one, and then we'll wrap it up. One benefit was, now that I'm making and breaking both lines, the capacitor here no longer has a direct link back to your switch. So in previous videos I was saying, well, you know, it just always seems to stop at 80 volts. And then I remember, well, these are 80 volts is the max on these things. And it was just spilling backwards, you know, over the switch there. And fortunately I didn't ruin anything. But now you can go up to, you know, these are probably 640 volts or whatever, so you can go a little further. So I did just want to look at that trend again of seeing improvement with voltage, and I'll show you what I've got there. 4 milliamps, 4 volts, 20 milliamps, 80 milliwatts. 9.25 volts in your spike, and it's across a 10,000 ohm resistor. And so you can, from there, calculate that you're getting back 8.5 milliwatts versus your 80, so 10.6%. Now you go to 6 volts and you get that many milliamps, that's your input. The spike jumps up to 15.7, and now you're getting 15% back. So recall a couple of videos ago when I kind of threw up my hands, I was saying, well, this is I'm only getting like a total of 21% efficiency back. And sometimes it's kind of good to throw up your hands, because I've just about doubled that now. You know, it's still not anything great, but moving in the right direction. So this pattern with voltage, I wanted to see, does that continue? And so here, 8 volts, that back, boom, 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 boom. I ran it all the way out to 28 volts, and you're getting 38% back, 39% back from your spike. To end this video, and then in the next one I'll do the bipolar commutation. To end this video, let's crank it up again, and maybe see if I can, you know, have it twice as good as my last, because that's what I'm looking for, is incremental improvement. So can I go from 20% to 40%? I made it out to 38.8. So let's crank her up and see what happens. And now we don't have to worry about this thing bleeding over. Okay, so first we'll look at it at 28 and see if this setup is a little better. And then I think we can get away with going to 30. I'm not going to go past that because I don't want this thing to fly apart. This is my test bed. I don't want to get hurt. Like I said, I think, you know, be it like 3,000 RPMs, you might get hurt. But still, I don't want this thing to blow up and then I have to start from scratch. Come on. Looks like it. Well, 1843. Yeah, 1843. Last time we were at 1654. So I didn't have everything exactly the same. So we're drawing 100 milliamps instead of 90. We're spinning it, as I said, 1843 instead of 1654. The spike is 104 instead of 98.9, 38.6% instead of 38.8%. Do we dare go faster?